about, and that was a great question from Marco about what is the intent of this workshop. And I'll just sort of summarize that real quickly, and then we can start with the introduction to my particular project, which is the most recently funded CROSS project. But again, this workshop is around topics of interest related to autonomous vehicle control and autonomous vehicles in general. And so we have a diverse set of speakers. I'll give a quick overview of my project, which is related to sort of a vehicle agnostic, if you will, autonomous vehicle control. We'll move to a topic around open source tools available for, in this case, Quadrotor development. And then we will move towards an autonomous surface vessel project, particularly related to attitude, heading, and reference systems. And then we have two topics related to some of the communication and infrastructure issues associated with autonomous vehicles in general. So with that, Stephanie, I think you can roll my video. Welcome. This morning, I would like to talk about the newest funded CROSS project, my own project, which is titled the Open Source Autonomous Vehicle Controller. A little bit about me. I am a third-year PhD student in computer science and engineering. My focus so far has been primarily on control theory and embedded systems. And prior to graduate school, I was a principal member of the technical staff at Applied Materials Incorporated. My advisor is Professor Gabriel Elkaim. Of course, he is the director of the Autonomous Systems Lab at UC Santa Cruz. He's a recognized expert in the field of embedded systems and mechatronics. And of interest here is under the tutelage of him and through his lab, the Slugs autopilot, which was an early open source UAV autopilot, was developed. To a great extent, my work here will build upon the success of that project. So by way of background, autonomous vehicle control is obviously a very active research field. You can see in the images above 3 different types of very, very different vehicles, from the UC Berkeley legged robot on the upper right to an autonomous vehicle in the middle picture to a novel water-going quadcopter that's being developed down in Monterey. They exist, of course, in pretty much every environment, both terrestrial and extraterrestrial, if you want to consider spacecraft as well as the Mars rover, for example. One thing that all of these vehicles have in common, however, is that they all utilize a real-time embedded controller. That is to say, they have a controller which takes in sensor data, estimates the state of the vehicle, and based on that state estimate provides some action that it takes in the world, whether it to change its direction, to increase its speed, to move its limb, whatever. They all have some form of real-time control. In addition, most of these applications, at least certainly the ones that are under development today, they also have a much higher level of control and interaction. And they use multiple computers for this. For example, they might have a computing module that performs some sort of optimal guidance control and navigation. They might have a computer that's dedicated to measuring and interpreting the world through computer vision, or they might have a LiDAR measurement. They might have some non-real-time needs for communication to a ground station or to other vehicles. But what is essential in all of these is that there is no common real-time platform for research and development of autonomous vehicles. That is to say, each one of these projects has developed its own real-time controller based on its applications. And that's what we want to try and change with this project. So the proposal, therefore, is that we want to develop an open source, real-time embedded controller for autonomous vehicle research and development. And in particular, we want this controller to be vehicle agnostic. That is to say, we want it to be useful for a larger number of vehicles than just a single class of vehicle, like an automobile or a quadcopter, but one that can be applicable to almost any real-time autonomous vehicle. And equally important, this controller will automate that data pipeline that will allow seamless integration to a single or multiple external processors that will enable those computationally expensive operations that I just discussed, such as computer vision, guidance, navigation, model predictive control, you name it. We have several objectives for this project, starting with simply defining specifications for this vehicle agnostic vehicle controller. We will develop an embedded hardware architecture and a corresponding modular firmware based on that hardware, both of which will use embedded programming and embedded hardware best practices. To demonstrate its value, we need to implement it on some vehicle ourselves, and so we plan to implement it onto a scaled automotive platform. We also intend to demonstrate the advantage of having that higher level control performing some more advanced computation. So we will demonstrate optimal control with obstacle avoidance or something like that on the vehicle. And then, of course, we need to publish our results for both the controller design, both hardware and firmware, and we want to publish the results of the actual vehicle testing results once we've completed that testing. I want to give you a quick overview of what the firmware architecture looks like. This is a block diagram demonstrating how we intend the data flow to occur within our controller. Everything within the grayed out box is what we intend to produce. That is the firmware that will allow communication to the supervisory controller or controllers up above, as well as to take input from a manual control down below. But fundamentally, the architecture is intentionally quite straightforward. It will take in real-time sensor data from the world. From that sensor data, it will provide an estimate of the state of the vehicle relative to the world. That is to say, its velocity, its position, its attitude, its pose, what have you. From that optimal state, then the controller will make some decision based on some guidance from a supervisory control on where it wants to go or what it wants to do in the world. And that controller will then provide the necessary commands to the outputs of the vehicle itself. These are typically going to be motor commands or servo commands, but they could also be digital outputs of various forms as well. The blocks in green are essentially modules within the firmware that are easily replaceable by the adopter of the architecture. In other words, if you are a vehicle controller and you want to provide your own custom state estimation algorithm, this architecture allows you to develop it and drop it in as a module into the firmware, simply by replacing a single file or a single couple of files. If you include the header. Similarly, if you want to have some, if you want to develop your own real-time control algorithm for the vehicle, in the same way, all you do is you simply replace a C file and its associated header. And thus, we think that we can offer an advantage over a more sophisticated but yet more limited approach that, for example, exists for UAVs today. From the hardware side, we have this block diagram. Again, everything within the main gray box is what we intend to produce as part of this project. In its simplest form, it's a microcontroller and an internal sensor, an IMU, which estimates it measures its state relative to gyroscopic forces as well as inertial forces. And in this case, it will also have a measurement of the magnetic field. So it basically is a so-called 9 degree of freedom measurement unit that estimates its state relative to those. Additionally, however, of course, it will take external sensors, and we will define several of them utilizing the most commonly used interface protocols for sensors, mostly digital sensors these days. For example, a vehicle might require a GPS unit. It might have a need to know its altitude, so it might have a barometer. It might be measuring the motor speed or the joint angle of an actuator. And so it might need an encoder measurement. And so we'll provide examples for many common interfaces and many common devices. And then the microcontroller will also provide a variety of outputs, the most common of which would be a PWM signal or a digital signal. But there might be some user-specified outputs that they can provide as well. And there will be plenty of connectivity to allow that sort of output. And then it will inherently provide a connection via some form of high-speed serial to a higher level processor or multiple processors. Additionally, it'll have a dedicated channel that can communicate via radio to a ground control station, such that it can mimic the usability that is done for UAVs, for example. And then it'll have a manual remote control input as well for a human user to take over control at any point. To ensure that this technology is employed as widely as possible, we want to provide, not only do we want to take advantage of the robotics open source ecosystem, but we actually want to provide links such that other people can, using these open source applications, will be able to immediately apply them to our system. And in particular, there's two robotics foundations that seem to be the most widely adopted today. One is called the Drone Code Foundation, primarily formed around UAV operation. But there's two applications in their portfolio that we intend to use and implement on our controller. One is a lightweight protocol, extensible protocol known as MAVLength. In fact, Slugs was one of the early, the Slugs autopilot developed in Gabe's lab was one of the early influencers of that particular communication protocol. Drone Code also produces an open source ground control system called Q Ground Control that speaks to its autonomous vehicles via MAVLength, and we intend to use both of those things in our project. And then finally, or in addition, there is the Open Robotics Foundation, which has two main applications. One is called the Robot Operating System, or ROS, which allows your component to be integrated into a larger ecosystem of robots. So our controller will inherently be integratable to ROS, primarily actually through a link called MAV-ROS, which is a decoder that changes a MAV-length communication protocol into a ROS node. Additionally, Open Robotics has a very widely used and very capable simulator known as Gazebo, and we will be using that during the development phase. And then finally, of course, any kind of computer vision these days is done using open source software, primarily using OpenCV. So to the extent that we implement computer vision on our system, it will be on a computer running OpenCV. To provide sort of an existence proof of our approach, I found this paper from ETH Zurich, published in 2018, of an autonomous race car. That's pictured in the image in the upper center. More of interest relative to our proposal here is that it actually has three separate modular computing systems. One which is dedicated to computer vision, shown in the left-hand block of the block diagram. Then they have the so-called master computer, which is doing their mapping and their LiDAR data, as well as their sensor fusion, all in a separate computer. And then they have the real-time computer known as the ECU in this case, which is doing the real-time control based on the guidance from the master computer. And to be clear, what we're proposing is the real-time component of a system such as this. And the only major difference here with our proposal is we're both using a distributed architecture, but with our proposal, all of the real-time sensor data, in order to really enable best practices real-time control, will be coming in through the real-time computer. The exception for that might be the LiDAR, or more likely the camera might be implemented separately from the real-time computer, but almost all of the other sensors should come in into the real-time computer. These are what we've defined to be the vehicle requirements for our test vehicle. Like I mentioned earlier, we want to choose an automotive platform. And so something like the image on the right, where we have a scaled electric car, rear-wheel drive electric car. The sensors required to operate this vehicle will be the motor velocity, or velocities in the case of a dual motor car, the steering angle itself, as well as some localization technologies. A GPS will almost certainly be implemented. The IMU, which I discussed, will be part of the project, so it inherently is there. And then the potential for LiDAR or machine vision will be integrated for the higher level control that we discussed earlier. So that's it for the main proposal. Of course, I have more data regarding milestones and objectives and things of that nature, but I really wanted just to give you a sense of what our project is and what it entails. And with that, I would like to open up the floor for questions. Thank you very much. Okay, so that in a nutshell is our proposal for CROSS, and they were generously and courageously willing to fund it. So for that, I'm very grateful. So are there any questions for this particular project, or shall we move on to the first invited speaker? Feel free to unmute yourself if you have a question for me.
Hi, I have a question.
Yeah.
Oh, you're speaking about your optimality. Well, you're optimizing something.
Oh, so I mentioned optimality in the context of state estimation, but I also mentioned optimality in the context of a guidance algorithm. And so for the state estimation, that's essentially solving the best mixture, using some form of a Kalman filter, an extended Kalman filter will give you the best state estimation. But I think your question really is related to sort of the guidance and optimal guidance technique.
Right.
And I have been looking at several different forms of that. And in particular, there was a talk, I don't know if you attended it yesterday, from a gentleman from Samsung who's been looking at different ways of providing convex optimizations of different heuristics. That's something that I'm really interested in looking towards, but I'm a little ways out from that because the first thing I have to do is actually develop the test vehicle. But something along those lines where you're able to perform some path planning and then optimize it around a heuristic, whether that's time-based or whether it's energy-based or what have you.
Right.
Does that answer your question, Marco?
Yeah, definitely. Who is this gentleman you're speaking of? That I didn't catch that talk.
Oh, yeah, it was given by Brian Padden, and I can put a link to his research paper that sort of summarizes those results. I can put that in the symposium there.
Sure. Yeah. Thank you, Aaron. Appreciate it.
Okay. Any other questions? If not, then I would like to introduce our next speaker. Let me get to here we go. His name is Adrian Martinez-Vasquez. He was born in Oaxaca, Mexico, and obtained his BSc in mechatronics from the Technical University of La Mixteca in 2013. He then pursued graduate studies at the Center for Research and Advanced Studies at the National Polytechnic Institute of Mexico in the laboratory UMI LAF MIA. That's very complicated. Obtaining his master's degree in autonomous navigation systems. And currently he is a PhD candidate in the EE department at the same institute. He has also been a lecturer of autonomous at the Autonomous University of Mexico City and the Technological Institute of Tlalnepantla, teaching control theory and linear dynamic systems. He will be presenting today on an overview of open source robotics tools for quadrotor control and development, and using those tools that I mentioned in my talk, ROS PX4, which is an autopilot system, and Gazebo. And with that, Stephanie, I think you can roll Adrian's presentation.
Hi everyone, and welcome to the presentation overview of open source software tools for Quadrotor, control development, ROS, PH4, and Gazebo. My name is Adrian. I'm from Mexico. I am studying my PhD in electrical engineering in the Center for Research and Advancing Studies of the National Polytechnic Institute of Mexico. I would like to start with giving a review of the topic that I'm gonna cover. So I would like to present to you the current days of drone code, open source platform. I would like to go through the robot operating system, ROS, and also I would like to talk you the message definition exchange between companion computer and the flight controller, the architecture overview, and also I would like to talk you about some simulation where I show you a small application with a control law and a trajectory tracking of a quadrotor drone. I show you then a couple videos where I show you a simulation and a control the quadrotor using ROS, Gazebo, and a ground control station, and also a real flight with a quadrotor in outdoor environment, controlling through messages between companion computer and a drone with ROS. Finally, the community feedback. Drone code. I would like to start with talking about the drone code open source platform. The drone code is an open source platform for UAVs. The platform includes the core software components like PX4, the core autopilot, MapLink, the communication protocol between drones and the ground, and ground control, the ground control station software. Using compatible open source hardware like Pixhawk, developers could build complete drones in a wide array of shape or airframes. PX4 is an open source flight control software for drones and other unmanned aerial vehicles. The project provides a flexible set of tools for drones, developers, and share technology to create tailored solutions for drones application. PX4 provides a standard to deliver drone hardware support and software stack, and also with the use of autopilot hardware like Pixhawk, it's possible to assemble an air vehicle or any type, including even fixed wing vehicles or land vehicles. Now I would like to talk you about the robot operating system, ROS. ROS is a flexible framework for writing robots software. It is a collection of tools, libraries, and convenience that aim to simplify the tasks of creating complex and robust robot behavior across a wide variety of robust platforms. Why? Because creating truly robots, general purpose robot software, it's hard. From the robot perspective, problems that seem trivial to human often vary widely between instances of tasks and environments. Dealing with this variation is so hard that no simple individual, laboratory, or institution can hope to do it on their own. As a result, ROS was built from the ground up to encourage collaborative robotics software development. For example, one laboratory might have experts in mapping indoors environments and could contribute a world-class system for producing maps. Another group might have experts in using maps to navigate, and yet other group might have discovered a computer vision approach that works well for recognizing small objects in clusters. ROS was designed specifically for groups like this to collaborate and build upon each other's work. The implementation of the adaptation methods is done using ROS. That it is a framework that provides different tools in order to communicate with the robot. In this picture, I show you the organization of a simple structure that uses ROS in order to communicate. A node is an entity that is interested in publishing and receiving messages from other subsystems. For example, the robot or the computer controlling the robot. These nodes communicate through channels called topics and on which messages can be published. Nodes can either subscribe, be notified every time a new message is published on the topic, or advertise, publish messages on the topic. The subscription and advertisement are managed by the ROS master unit. The map-ROS package enables map-link, extendable communication between computers running ROS. Map-link enables autopilot, and map-link enables ground control station. If we remember that map-link is a communication protocol between aerial robots and ground station, in this case, ground control station. So in concrete, we are interested in control the vehicles through these possible inputs, the position set points, the velocity set points, and the acceleration set points normalized through vector. The node that execute these messages run the application on the companion computer and then control the vehicles from the companion computer with the flight control in offward mode. For the Quadrotor, the particular messages that we can handle are geometry messages, post-stamped, where you can give a position according to inertial frame. In this case, the point that the GPS registered where the vehicle was turned on. Also, with geometry messages twists, it's possible to control the vehicle through the linear velocity according to the inertial frame. On the other hand, with the map ROS messages, attitude target, you can control the vehicle through the orientation angles given in the notation of quaternions. And finally, the map ROS messages attitude target also can control the altitude through the messages, the normalization through vector. The definition of the messages to control the vehicle are according to this structure. For the case of the post-stamped messages, we have the position given in 3 coordinate axes in the orientation, where we have 4 parameters to make up the quaternions. The twist messages, we have a structure that contains the linear angular velocities regarding to the body frame on the vehicle. For the attitude target messages, where we have where we can control the orientation and the altitude of the vehicle through the quaternion vector and the thrust parameter. The communication between each node are made according to this picture, where in the picture we can see the offward node, which is each our application, where the control law as are execute. In this example, our application only communicates with the state topic and the set point position topic. In a simulation, ROS can be used with PX4 and the Gazebo simulator. It uses the MapROS Map-Link node to communicate with PX4. The ROS Gazebo integration with PX4 follows the pattern in the diagram. This shows the generic PX4 simulation environment. PX4 communicate with the simulation, for example, Gazebo, to receive sensor data from the simulated world and send motor and actual values. It communicates with the ground control station and offward, for example, ROS, to send telemetry from the simulated environment and receiving commands. I would like to present to you a simulation using a dynamical model of a quadrotor, where the dynamical model is given according to this equation. For now, we are not interested in delving into this equation, but we are interested in knowing the control input of this system. For our simulation, we will use the altitude messages, where we need to decide angles. The control technique using in this application for the moment is not important. In this graphic, we present to you the simulation result of a tracking trajectory control of the vehicle, where the blue is the desired trajectory and in red is the trajectory of the vehicles. So now I would like to show you a couple videos where we run the simulation using the ground control station and the environment Gazebo. In this video, we prove our application where we programming the control laws.
Off-board flight mode. Armed.
And now start the trajectory tracking algorithm running the offward node. We can see the ground control station. We receive the messages of the position of the vehicles. And in the second video, we proved the real platform built on the laboratory with the autopilot Pixhawk. This vehicle is only controlling through the companion computer where ROS is running, and all the nodes included our application. The experiment only consists in send messages through the post-stamped position topic given a fixed coordinate in space with respect to the frame or references fixes in the earth. the video I show you that I don't use the radio control. The vehicle only is controlling with ROS through the radio frequency telemetry. Work in progress. First of all, real-time implementation in outdoor environments. Due to the pandemic, I didn't have enough time for trying trajectory tracking in my laboratory in a real experiment with the vehicles. I could not execute a different application in my vehicles. And the second is connect the system to indoor environments with use of optical motion tracking. Connect the system to indoor environments with use of optical motion tracking is important because we can introduce another kind of application, like in particular doing obstacle avoidances or transport slum load. That is my principal topic in my PhD studies. Thank you for your attention, and if you have any questions.
Okay, great. Thank you, Adrian. That was a very interesting and rather, I want to say that was a rather timely and relevant presentation considering the introduction I gave in my talk to Ross. Does anyone have any questions for Adrian? I don't see any in the symposium minutes, but if you want to unmute yourself and ask directly, feel free. So I actually have one question, and that is, Adrian, if you could expand a little bit on what your a little bit more on what your PhD thesis entails and what you intend to demonstrate.
Hi, everyone. First of all, I apologize for my basic English. My mother tongue is Spanish. Can you repeat the question, please?
Yeah, I'm just, you mentioned at the end of your talk that you were, that something about your PhD research topic. I'm wondering if you can expand a little bit on what your ultimate research goal is with your work.
The principal objective in my PhD is to develop a control law theory, in particular in application of UAVs, unmanned aerial vehicles. And the topic, the principal topic of my thesis is to transport a slum load with a quadrotor. If we talking about the system or the dynamical system, is to move like a pendulum that swinging in the earth, attaching to in the quadrotor. We are interested in move this dynamical and make a control out that make this trajectory, for example, with the minimum swinging of the pilot. In the experiment, we are interested to develop application in outdoor environments. In our laboratory, we think that is a very hard application because many application is doing using OptiTrack or cameras in indoor environments. But if we translate the application to outdoor environments, where you can use, for example, sensors like GPS. For example, in this moment, I don't have a solution for measurement the angle or swinging of the slingblade, for example. We are interested in introduce another computer with a camera for make to get lectures of the swinging of the swinging pilot, for example. That is a work in the future.
Great. Oh, that's really interesting. So basically you're trying to figure out a way to control a load hanging off of a quadrotor, and you don't necessarily know its own motion. So you're trying to estimate that with optical means. Okay.
Yes.
Excellent.
Yeah.
Great. Does anyone else have a question for Adrian? If not, thank you very much, Adrian. I very, very much appreciate your participation in this workshop.
Okay.
It's really
Thank you.
quite interesting work.
Thank you.
Okay. Let's move on to our next speaker. This is one of my lab colleagues, Pavlo Vlastos. He is a PhD candidate along with me at the Autonomous Systems Laboratory. He is studying autonomous systems and control. One interesting thing about Pavlo is he was born in Greece on the island of Crete, but he grew up in Casper, Wyoming. His hobbies include launching autonomous boats, designing rail accelerators, and biking around Santa Cruz. And Pavlo will be speaking to us about an attitude heading reference system validation technique that he developed in the course of his work on autonomous surface vehicles. And if you would, Stephanie, if you could roll Pavlo's video.
All right. Hello, everybody. Welcome to today's presentation. My name is Pavlo Vlastos. I'm a PhD candidate at the University of California, Santa Cruz, and I'm part of the Autonomous Systems Lab. So I'll be talking today about attitude heading reference system validation. So a brief introduction. We know that we're seeing more and more cases of autonomous vehicles in daily life. Recently, the FAA approved Amazon to use drones to deliver packages to customers. And those kinds of vehicles have a lot of things to consider when we're designing them and building them. Obviously, there's fabrication, manufacturing, system integration. What kind of sensors do we need? What kind of actuators? Are we using a computer or something smaller like a microcontroller? You know, what are the power systems doing? How are they designed? And then from a theoretical standpoint, we have to be able to model that autonomous vehicle, the physical nature of that system. We have to be able to describe mathematically. And that might not be necessarily a vehicle at all. It might be a different kind of robot, a robot arm, a satellite. It varies a lot. But in addition to modeling these kinds of systems, we have to be able to control them. And there's a whole branch of study into, you know, what kind of control can we use. Commonplace, we see the PID controller, but more advanced controllers exist, such as, you know, optimized full state feedback and various other controllers. But part of designing an autonomous vehicle or robot or a system that needs to be able to operate in three-dimensional space and navigate is we have to be able to estimate the attitude and the orientation of that vehicle or of that system. So I'll be talking about attitude, heading, and reference systems, and how can we make sure that they're working? How do we validate that they're working? And I'll be referring to that system as an AHRS for short. So one of the helpful things to understand when we talk about attitude estimation and control, for that matter, of a vehicle is we have to know the vehicle reference frame. And for a robot arm, this might mean that we have multiple reference frames for every link in the arm. For a satellite, it's going to be similar to a vehicle, same for other things like rockets. And in this example, I'm showing an autonomous boat. And we have it doesn't necessarily have to be autonomous for the sake of showing the vehicle reference frame, but I'll explain more about why this specific example is used later. So we have the axes of rotation and the directions of motion. So we have, if you're going up and down, we have heave. If you're moving back or forth, that's surge. And if you're moving side to side, that's sway. That's specific to a boat. And you'll notice that if you've seen vehicle reference frames like this before, for different vehicles, the reference frame is sometimes flipped or has a different orientation. Sometimes you'll have, usually for aircraft, the z-axis is pointing down. But you still have yaw, pitch, roll for all of these vehicles. So when we are measuring the rotation about these axes, we want to find our Euler angles with respect to the inertial reference frame and the vehicle reference frame. And generally we use something like an IMU, or in this case, it's a sensor head. And we have to be able to calibrate the measurements that this sensor head gives us. So for this specific PCB here, this has on board an accelerometer, a gyroscope, and a magnetometer. And it has, each of these sensors, it has three, one pointing in each direction of the vehicle reference frame. Now, it gets a little complicated because some of the sensors, such as the magnetometer, might have a different orientation for its frame, where the x-axis is pointed opposite, or the whole frame is flipped, and that's something that you have to account for. Now on the right here, we see that we've collected this sphere of data, and this is accelerometer data that's collected in each axis, and you can plot it in 3D. And if you're doing calibration for these sensors, which you have to do, you'll want to allow the sensor to kind of paint around the sphere and hopefully cover it. And we see there's a lot going on here. We have this dark blue sphere inside, and we have these lighter data points on the outside. And so what's happening is we are calibrating our sensor head. We are collecting a lot of data, and then we're finding how much is it offset from where it should be. So where should it be? Well, ideally, when we rotate the IMU, or the sensor head, we should be able to have this unit norm vector that is always on the surface of that imaginary sphere. And that makes sense because if we rotate this, we would expect that the direction and magnitude of gravity is going to change in direction, but it'll maintain the same magnitude, and it shouldn't be changing a lot. Ideally, it shouldn't change at all. So we collect this data here shown in blue. This is the pre-calibration data, and we apply a number of different mathematical approaches to project, to correct the data onto the surface of the sphere. And we can find our offsets in the X, Y, and Z axes for those sensors, because they're not going to be perfect. Now, this histogram on the right shows how we are moving the number of data points from being offset by some amount in X, Y, Z, and this is the norm of those of that three-dimensional vector composed of those three elements, and we are able to shift it so that most of the data points are now on that sphere. So this is one of the steps you have to do in order to calibrate your sensor. But once you have it calibrated, you have to have a system to determine your attitude and to determine your orientation. So we have a problem that is intrinsic to the gyroscopes, which is, unless you have extremely expensive gyroscopes, and even then, they're going to drift. And usually it's as a function of temperature, but also it's inherent to when we try to find, our Euler angles, and we're trying to integrate our gyro rates, we're going to accumulate some error because we don't have infinitely fast sampling time. So we have to correct that gyro drift. If they didn't drift, in an ideal world, we would be able to integrate them and obtain exactly our rotation with respect to the inertial reference frame. So this symbol here, we have omega sub y, that represents the vector of gyro rotational rates. And what's happening here is we form a skew symmetric matrix, and then we read in our, either from our accelerometers or our magnetometers, we take that sensor measurement in all three axes, we generate a rotation matrix depending on the sensor, and we find the error between how much have we rotated with respect to gravity. We project it after scaling it onto that skew symmetric matrix, and then we integrate that. And what this algorithm is doing, this is called the complementary filter, is it is generating an estimate of our rotation matrix, shown here as r hat. Now, you'll notice that r hat is being transposed and then fed back here, and that's where we get the error. Ideally, if our estimate of the rotation with respect to the inertial frame is exactly what our rotation as measured from gravity is, we will have an identity matrix, and we won't be effectively projecting any error onto our rotational rates before we integrate them. But there's always going to be some amount of error, so this feedback loop helps correct for the gyro drift. So there's a bit more math to it. When we do this integration, we can do it a couple different ways, but one of the most effective ways is the what's known as the Rodriguez exponential integration, and that's shown here as a three-term Taylor expansion approximation. And here we have the anti-symmetric projection operator, and that's happening here. So we find the difference between what our sensors measured for the rotation and what our estimate was, and we can project the difference in the form of a matrix onto our rotational rates. And that's, again, that's formatted as a skew symmetric matrix. Once we have this matrix and we've done all of this math, we can then extract our Euler angles. And so that's what's happening here. We can get our yaw angle, our pitch angle, and our roll angle. Now notice here I've indexed these by 1 through 3, but depending on your formatting for a code, this is sometimes indexed from 0 to 2. But the point of all this is this complementary filter is going to be used to estimate the vehicle attitude. And part of that is from extracting those angles. So once we do this and we apply our complementary filter, or perhaps we have a different one, such as a Kalman filter, we have to validate that Ahers. So the complementary filter is part of the Ahers along with the IMU sensor head, and we have to make sure that it's actually working. So we could compare angular rates. We could compare the angles themselves, the Euler angles. So if you have a lot of money, you are able to do this using a rate table. You can compare on each axis. You can rotate a very large, very well-machined gimbal so that you can have your yaw, your pitch, and your roll. And you can find those rates directly with these external sensors in this gimbal and compare them to what your Ahers is doing. And ideally, the difference is 0. Ideally, they are the same. So what I worked on was a validation apparatus that did not cost as much money, but could still be useful for smaller projects that require developing your own Ahers. So here we have a laser cut MDF frame that's holding an IMU, an encoder, and a microcontroller. And what's happening is we are able to measure within just a single axis the roll angle, and we can measure that with the encoder and compare it to the IMU sensor head and the onboard Ahers. So And this doesn't necessarily have to be on board. You could also collect all this data and then process it offline too. But we can also rotate the sensor head mount so that we can vary the contribution of these external aiding vectors. And that can include gravity or the magnetic field in this case. Now for satellites, they can use the sun as an external aiding vector, but that's a whole different story. We can talk about that after the presentation. Notice here that there are a couple different ways that we could orient the IMU. We could actually test for the yaw angle. We could test for the pitch angle. And so this can be detached and then placed back on in a different orientation to isolate that axis of rotation. So here's some data collected by this apparatus. In green, you can see the encoder angle over time. And in red, you can see the roll angle from the complementary filter over time. You can see that there's pretty good agreement, and ideally, they should overlap exactly. On the right, we see this is output from the complementary filter and the encoder from the apparatus, and now it's positioned at 90 degrees. So this is highlighting the fact that at 90 degrees, your external aiding vector for gravity is not going to contribute to your orientation estimate because it is now parallel with your roll axis. And that is a good indication that your AHRS is working. If you were oriented at 90 degrees with your roll axis and you saw that gravity was contributing, then you might have a problem with your calculations. So another test we did after applying this apparatus and tuning our complementary filter is we put the system, the IMU, the microcontroller, and the GPS on a small remote control boat. And we took some GPS data. One of the measurements that GPS data can give you is called the course over ground angle, or COG. And that is the direction you are going, the angle of that direction with respect to a local tangent plane. This is a very useful measurement to have because we could compare it with the yaw angle over time from the complementary filter. And that's what we see here. In red is the yaw angle from the complementary filter, and in green is the course over ground angle. There's pretty good agreement, but you can see that there are larger errors in some of these areas. However, this was useful to do in order to validate that over a long time, the direction is the same, and that potentially we could use both the course over ground angle as well as the yaw angle for autonomous navigation. Now for a boat, this is relatively simple. For aircraft, where you're dealing with all dimensions, you would have to collect data for each axis, and that can get a little bit more complicated. So I'd like to thank you for listening to this presentation, and I'd be happy to answer any questions at this time. I hope you enjoy the presentation.
Okay, great. Thank you, Pavlo. Very interesting topic, and again, very timely. Let's see if I don't see any questions in the symposium minutes. If anyone has a question for Pavlo that wants to just unmute themselves, feel free right now.
Hello, good morning. I have a simple question, please. Pablo, great presentation. Thank you very much. My question is, have you evaluated how long or what is the delay in the measurement? Like, for example, if you're using a real-time system, how long does it take for the, the change to be correctly estimated? Thank you.
Oh, yeah, that's an excellent question. So if we're just dealing with the AHRS itself on the microcontroller, the delay is less than 500 milliseconds. I think we can. We're operating sometimes at a frequency is up to at sometimes 100 hertz, usually around 50 hertz. With the course over ground angle, there is a significant delay between the the angle from course over ground compared to the angle of the like the yaw angle, and that's because the course over ground requires that you have to be moving before that angle is calculated, whereas with the complementary filter, that orientation is known at your operating frequency. That's an excellent question.
Okay, thank you very much.
In addition, the course over ground is coming from your GPS, which is, you know, at 1 hertz or something. Is that right, Pablo?
Yeah, that's another good point. That is coming in at a slower frequency, and that's exclusive to the GPS. Yeah.
Interesting. Okay, does anyone else have a question for Pablo? I have hopefully what is a quick question, Pablo, and that is, your apparatus that you built measures the static angle. Is there a way to, either using the vehicle itself or some other inexpensive mechanism, to estimate the rate? You mentioned that the gyro tape, or I guess it was the rate tables, can actually measure the real-time change in the angle, meaning for time derivative of the angle. Do you have a mechanism for estimating and validating that as well?
So that's one of the things that that I want to incorporate on the apparatus as we expand it. So what we could do right now is we can use the encoder, and we can calculate the rates with the change in encoder angle over time. So that comparison could be done, but we don't have a way to directly measure the angular rates with the apparatus as it is now. But that is something that we could definitely do. Maybe even a Hall effect sensor could be used.
Interesting. Great. Again, Pablo, thank you very much. I appreciate you putting the time into the presentation. It would have been real drag if nobody presented in this conference. Thank you.
Thank you.
And now I want to move on to our next speaker. Our next speaker is Shesha Sreenivasamurthy. He is currently employed as a principal engineer at Nebula Technologies, and he has many years of industrial experience, but he is going to talk to us today about his PhD research under Katya Obraska in the Department of Computer Science and Engineering at UC Santa Cruz. And his presentation is entitled Towards Biologically Inspired Platooning for Autonomous Vehicles. With that, Stephanie, if you could roll the next video. Thank you.
Hi, my name is Shesha Sreenivasamurthy, and today I will be talking about biologically inspired platooning for autonomous vehicles. Brief agenda. What is platooning and why platooning, its types, and our main contribution, which is biologically inspired platooning, a short demo, and preliminary results. So what is platooning? According to US Department of Transportation, platooning is a coordinated operation of 2 or more vehicles via cooperative adaptive cruise control, or as Mid-American Association of Transportation officials would define it, it's a practice of electronically coupling multiple devices in order to significantly reduce the gaps between the vehicles. So what does this reduction in gap achieve us or give us? It gives us fuel efficiency, because when the gap reduces, it reduces the air drag, which improves the fuel efficiency and also reduces carbon footprint. It also improves road capacity. And Federal Highway Authority reported around 5,000 fatal truck crashes in 2018. And the major reason for these crashes are driver fatigue and distraction. And when we are dealing with platooning, there is some degree of automation involved, which will reduce the driver's fatigue. So it will improve the safety. Coming to automation, the Society of Automotive Engineers have defined 6 levels of automation, 0 being the least, 5 being the highest. And for autonomous platooning, we need at least level 4 automation, wherein the human drivers will relinquish their control when they are joining the platoon, and once the vehicle is in platoon, it is autonomous. Platooning can happen either on freeways or in cities. When you are dealing with city roads, there is an additional challenge because of the traffic signals and the traffic rules. So for that, the vehicles have to constantly communicate, and there is a higher level of interaction with the infrastructure. So in this work, we focus on freeways. And the platoons can happen either as an offline process or in the entrance of the freeways or autonomously during the trip itself. If it happens autonomously during the trip, then it has to support some of the basic maneuvers, such as joining the platoon, exiting from the platoon, changing lanes, or splitting the platoon, and also merging of platoons when the lane merges too, right? So depending upon where these maneuvers happen, it can be classified as either centralized or decentralized, or in a decentralized, it can be deliberate or emergent. We'll go into a little bit details about these in the forthcoming slides. The centralized platooning is characterized by the presence of a leader, and generally it will be the first vehicle, but need not be. And this has got a lot of some of the issues, or it has got disadvantages, which is it's a single point of failure, serialization, and also a shorter platoon length, because the first vehicle has to communicate with the last vehicle. And the longer the platoon, they introduces communication delays because of the higher packet drops and retransmission. These issues are mitigated by the use of decentralized system. And in general, the objectives or the maneuvers are first identified, and the messages required for those maneuvers are developed. This is a typical top-down approach. An alternative method is inspired by nature, which is a bottom-up approach called the emergent behavior. So our platooning system is motivated by termites, which are very sensitive to environmental changes. And whenever they sense the change, they mix the dirt around them, and then they will, which contains a chemical called pheromone, and deposit at the place where they sense the change. And if any other termite find a pheromone-soaked dirt around them, and they will do the same. So these are the simple rules each termites follow. And this kind of indirect interaction is called stigmergy. And you can see that there is no supervisor supervising their activity, but every action happens at the local level. And with just local interaction, a global behavior emerges, which is a complex termite mound being built. This is called an emergent system. And in nature, pheromones naturally fade due to evaporation if it is not constantly replenished. So drawing parallels with emergent platooning, each vehicle in our system broadcast their state, which includes position, ID, which can be a VIN number, and also the globally unique platoon ID, which is a UUID. And most of their communication happens indirectly without direct communication, which is drawing parallels with the stigmergy. And each vehicle uses gap pheromone messages from two of its predecessors, or keep track with the messages from two of its predecessors and a successor. Using this information, each vehicle calculates the speed of the two predecessors and also intervehicular gap. And this speed is used to adjust its own speed. The speed of the two predecessors is used to adjust its own speed. How the position is used in order to determine the speed is given at the right-hand bottom corner. And I'm not going to go deeper into those equations in the interest of time. And the pheromones are just the reciprocal of the gap. And we can see that the rate at which the predecessor pheromone fades is different or significantly higher than the successor pheromone. This is to prevent the exiting vehicle's predecessor to prematurely establish itself as a tail or the last member of the platoon and give a chance for the exiting vehicle's follower to catch up, right? So that is why there is a difference in the rate at which they fade. So this is very similar to how pheromones fade in nature. So we can see that we drew parallels with stigmergy, and we drew with pheromones fading. And now coming to rules, similar to how each termite followed some rules. So we follow the speed rule to maintain the speed. And for example, we use the catch-up rule for the vehicles to catch up. Say, for example, if the vehicle exits, then there is no communication that happens between the vehicles, but just because of the vehicle exited, it is not transmitting any more pheromone messages. So the actual pheromone value falls below a threshold and the vehicles catch up, right? So with just local interactions, a global behavior, an exit maneuver behavior emerged. Similarly, we use the tail rule in order to make sure that to establish itself as a tail member, or similarly the first member. And lastly, we use the alignment rule for like whenever the lateral distance between itself and the predecessor goes beyond a threshold, then the vehicle aligns itself. Say, for example, where the first vehicle changes its lane, because of the alignment rule, the second vehicle changes and it's followed by third, and so on and so forth. So without having any workflow, we are now having a behavior, which is the lane change behavior, which is emerging, right? So why do we have to go with emergent systems? First, because one of the reasons is lower maneuver time. So we can see that the emergent system is much faster when compared to a centralized system or a deliberate system when it comes to exit maneuver. And also, as I noted earlier in my previous slide, that it does not require any explicit message exchange or a workflow to be implemented, and the behavior or the maneuver emerges from by just virtue of following the basic rules. So it becomes less complex. So that is the reason to go with emergent system. Now we did some experiment using Plexi, which is an extension to Vanes, and which uses Sumo, a traffic simulator, and Sumo uses Omnet to simulate every vehicle as a mobile node. And Plexi provides a centralized join maneuver, and we extended Plexi with centralized exit maneuver. And also Sumo also provides a leader predecessor controller, which is a centralized controller, and in order to adjust its speed. And we extended it with two predecessor controller by using the information of just two of its predecessors, so that it can become a decentralized rather than being a centralized system. And we evaluate with 20 vehicles join and exit maneuvers. And also we compare our emergent system against the centralized system. Now our performance metric is maneuver latency, where the join maneuver latency is defined as the time between the vehicle entering the system and being a part of the platoon. And the maneuver latency of exit is defined as the time the vehicle's intention to exit and not being a part of the platoon. Now I have a brief demo, which while doing so, I will also explain the experimental setup. So we can see this is a simulation in Plexi, using Plexi. So we can see that every 2 seconds a vehicle is entering the system, and the second vehicle is now catching up with the leader. And now when the leader is coordinating its maneuver to join the platoon, if the second vehicle sends its interest to join the platoon, the leader will explicitly reject it, saying that because it's in the middle of the platoon. So there is a serialization. So on and so forth. Every vehicle will join the platoon. Like I just have 5 vehicles in the interest of time instead of 20. And once all the vehicles join the platoon, all the vehicles, but for the first and the last vehicle, will show their intention to exit. At that point, they will all turn blue, and serially they exit the platoon. And once they exit the platoon, they turn yellow. So we can see that it happens at around 60 seconds. Now it's almost time. Okay. So all the vehicle exited, and now the last vehicle will now communicate with the first vehicle that it has exited, and during which time it has said that it is going to exit. And now they all caught up, and now it's a platoon of 2 vehicles. Similarly, in emergent system also, it does exactly the same thing. And all 5 vehicles will try to communicate, will see the first vehicle will see that there is no pheromone, so it is going to catch up. And once it is nearing the first vehicle, then it will send some pheromones. So it will do a join maneuver. And similarly, the second and third and fourth and fifth. And once all 5 vehicles are there in the platoon, the exit maneuver is instantaneous because it doesn't have to communicate with any vehicles, and immediately they all change their lanes. And this happens at around 45 seconds, which we can see that, it is much faster when compared to the centralized system, right? So it's almost time. So now we can see, we will not even notice the vehicles turning blue. So they all changed, and now the vehicles have exited. And because there was a decrease in pheromone value, the last vehicle caught up with the first vehicle. So we have an emergent behavior which emerged from local interaction. So this is our preliminary results, where we see that in a centralized system. Okay, I need to talk about the backoff. So whenever the leader will reject a request from one of its for one of the vehicle, the vehicle will actually do a backoff. Say it waits for random amount of time before it can retry. So it constantly retries after some backoff. So the amount of time it takes for the last vehicle to join in case of centralized system is around 126 seconds. Compared to emergent, it is 83 seconds, 35% faster. The reason for that is serialization at the leader as well as the backoff. We tried different backoff values. Any value less than 3 seconds would make the number of retries so much that it will become almost the leader will be constantly trying out these trying to reject for all the 20 vehicles. So 3 seconds was kind of optimal for 20 vehicles. And as and when we increase the backoff, so the amount of time for the last vehicle to join significantly increased. So as we can see, so for our experiment, we chose 3 seconds. And similarly, when we are dealing with multi-vehicle exits, simultaneous exits, the centralized system took 2.5 seconds, whereas the emergent system is instantaneous. And more to the point, there is no explicit workflow that was required. So it will become less complex, which is very important. And now concluding my talk, what I showed was a novel emergent based platooning. And I demonstrated that on a real vehicular simulator. And according to our experiments, the preliminary results are very promising for emergent system. And there are a lot of future work, or lot of things that yet to be completed. For example, I need to compare with the deliberate decentralized system. Additional maneuvers needs to be evaluated. And also, we just use the tail, merging at the tail as our joining strategy. There are head and middle joining strategies. Joiner and the platoon being in different lanes, simultaneous multi-vehicle joins, and having obstacles during the maneuvers. All these needs to be addressed. So that is in our roadmap of our future work. Thank you for listening.
Excellent. Thank you, Shesha, for a very interesting talk. I had observed other sort of natural platooning behaviors, such as swarms of birds, but never thought about the idea of a pheromone trail and its inherent time-based decay. So that's a really interesting way to approach platooning.
Thank you.
Does anyone have any questions for Shesha with respect to his work here? Feel free to, let me check the symposium minutes. I don't see anything there. So yeah, just feel free to unmute if you have a question for him. Okay. If no one else has one, we are running a little short on time, and I don't want to short the next speaker, but I do have a question for you, Shesha, and that is, sure. Did you consider other forms of biologically inspired platooning when you approached this work, or were you impressed by the idea of this particular biologically inspired concept and wanted to pursue it further?
When you say this, do you mean to say termites, or what do you what do you
termites, or I guess ants probably do something similar.
Yeah. Yes. So I did a study with at least 5 to 6 different animals. For example, fish, ants, honeybees, and starlings. those are the different biologically. They have inspired a lot of people and how they emerge to form these kind of platoons. So, for example, if it is the starlings and fish, they are mainly used in when there is a lot of free movement, like say drones or underwater vehicles. And termites and ants are very similar, and honeybees are more or like a one-to-one communication when they are doing what they call as the dance. I forgot the name of the dance, but they do a dance using which they communicate, and there is a kind of one-to-one communication. It's not more, and the termites and ants were very, very close to what we wanted to achieve in terms of platooning. So that is why termites inspired us the most.
Great. No, that makes perfect sense, because ants and termites presumably.
Yeah, they have different kind of a little bit. Ants has very similar thing, but the use of pheromones in ants is slightly different. How do they protect themselves? And it's still you can. If we wanted to argue, we can say we can use ants and do similar kind of behavior, but it's just about I was more inspired with the complex building nature of termites, so we chose termites.
That makes really good sense. Yeah, no, it's a very very creative approach towards autonomous vehicles, and thank you very much for the presentation. Yeah, really interesting stuff.
So, and we submitted our paper. Today is the deadline for a vehicular network conference. So we submitted this paper
oh, excellent.
for VNC.
Yeah, great to hear.
2020 VNC.
Very good. Okay, let's move on then to our final speaker. Our final speaker is Anuj Kaul. He's another PhD student in Katya Obratska's lab, and he's been working on distributed network control plane architecture for autonomous vehicles. The name for his title for his talk is Dynamically Distributed Network Control for ITS. And with that, Stephanie, if you could roll the last video.
Hello, everyone. My name is Anuj, and I'm here to present our work on Dynamically Distributed Intelligent Transport System, also known as D2ITS. So at high level, one of the components of D2ITS is vehicular communication. And the job of vehicular communication is to send the information for self-driving, coordination of flow traffic, communicate the road conditions, collision avoidance, and so on. So these are the basic kind of functionalities a vehicular communication should do. Vehicular communications are divided into two types. One is vehicle to vehicle, other is vehicle to infrastructure. By infrastructure, we mean roadside units like a Wi-Fi access point or a base station like LTE. The challenges of ITS, which has a unique challenges, are low latency because the messages are in order of tens of milliseconds of latency, reliability, scalability, and geographic decentralization. What that means is like there is a high possibility that you cannot guarantee that vehicle is always connected to a wide area network. So there might be some zones where even though network is good, but the vehicle cannot communicate because it is overshadowed by buildings around it. So we need to have some kind of architecture which doesn't let this happen. So with that in mind, we came up with a new architecture. It was a new architecture, something like shown here, where we have a main controller, which is a controller maintained at the top level by the ISPs. This could be co-located with like an LTE base stations, which are constantly maintained by the network vendors. This main controller has a view of the whole network, but it delegates the control downwards. Next level is a secondary controller. Secondary controller communicates with the main controller through vertical east-west interface. We have borrowed the name from SDN terminology. Secondary controllers talk to each other through horizontal east-west interface, where they share both control plane message as well as data plane message. in terms of control plane message, these are the messages which could be like sharing what is the status of the controller, what cars they are controlling, if there are any other level of information like what kind of tertiary controllers they are controlling. That is the control plane message. Then the data plane message is an information which you want to share across. For example, if a vehicle wants to send message to other vehicle which is not in the same area, so the message might hop between secondary controllers until it reaches to the vehicle. Then we have another layer, other hierarchy, that is called tertiary controllers. Tertiary controllers have a unique functionality where they can have both and switch. They can act as switch as well as controllers. If they are acting as controllers, then it is their responsibility to control the nodes below them. But if they are not, they just act as simple nodes. The secondary controllers are like can use short range communication or mid-range communication like Wi-Fi access points. The tertiary controllers between the nodes can use something like IEEE 802.11p, which is short range communication. So this is a high level architecture, and I just want to reiterate that the depth of the controllers is arbitrary and it depends on the application. For example, in the next slide, we have ITS. So we have 3 depths of controllers, but if you have any other application, we can scale accordingly and increase the depth depending upon the application. So in this case, we have a roadside base station, which can be thought again as an LTE base station. There's a controller co-located with it. Then we have roadside units, again, as I mentioned in the previous slide, they are like Wi-Fi access points, and controllers are co-located with Wi-Fi access points. Then we have a third level where vehicles are acting as controllers and they are controlling the vehicles below them. And the blue circle I have shown here, they are calling it as domain, but it essentially is the range of what the vehicle as a controller can cover. Vehicles can communicate with each other, the control plane message as well as data plane message. So just to reiterate that the functionality which we are trying to hide here is that secondary controllers or even the main controllers or tertiary controllers can instantiate themselves accordingly. For example, if secondary controller is saying that it is getting overloaded, it can select a tertiary controller from a group of vehicles and tell it, okay, now you are the tertiary controller, you take control of XYZ cars. So from there onwards, the tertiary controller will take care of those cars, and only if required will communicate with secondary controller for the next level of hierarchy. So that is what we mean by control delegation here. So what is D2ITS? D2ITS is a dynamically adjustable and distributed control plane. It has lower latency and lower overhead. It's a scalable architecture and it can delegate the control, as I mentioned in the previous slide. And to add on top of it, the whole architecture is designed in such a way that it is network agnostic. So this was a high level overview of our architecture. Now we wanted to showcase a use case. So in this case, we took use case as road hazard warning application, also known as RHW. This is an application which HC came up few years back. They divided messages into 2 categories, what is called known as DEMS, decentralized environmental notification messages. These are the data plane messages from RHW perspective. They are subdivided into 2 categories. One is emergency, other is warning. Emergency messages are low latency messages and have a shorter area to be covered. So for example, if you have an accident, you just want certain vehicles like within certain radius to stop. You don't want that big radius for cars to stop. So that is what emergency messages are. Warning messages are more like roadside congestion, traffic information. Then they also categorized control plane messages, also known as CAMs. CAMs are mostly about the location update from the vehicle, speed at which vehicles are going through. And if new vehicle is coming in, the new vehicle is joining into this network, they need to send authentication and security messages. Those all happen under one umbrella of CAMs. So based on what HC defined, we decided that it makes sense for D2ITS to handle these 2 messages separately. So for CAMs, what our controller does is when controller receives a message, CAM message from a vehicle, it updates its local database information about the vehicle and also sends this information to the neighboring controllers so that they also know what is going around with the neighboring controllers and what vehicles are they controlling. So that's all what we do with CAM messages. For DEMS, once the controller receives a DEMS message, it checks a type. If it's an emergency message, then it just broadcasts to its own domain, the range to which the vehicles are connected. What would this mean is that we are making sure that the latency is reduced and we are not flooding the whole network, but just the domain of that controller itself. But if it is a warning message, what we do is, what the controller does is it computes the relevance of that message, if it is impacting the neighboring controllers or not. If it is, then the message is forwarded to the neighboring controllers. Otherwise, it is just sent to the controllers, to the vehicles of the controller, which are getting affected. So the next part of our design was to showcase the control delegation. So we took handover as an example, but handover is an overloaded term, and I just want to distinguish between the kind of handover we are talking about and what already exists in the networks like LTE, 3G. So I categorize what is happening in 3G and LTE as physical control delegation, where the link between the two entities is broken and a new link is established. I'm not talking in this work, we focus more on logical control. The logical control meaning how the vehicles move, how the controllers move their control from one of the vehicles from one controller to another controller, be it vertically, meaning secondary to tertiary, or horizontally from secondary to secondary or tertiary to tertiary. So we decided the two kind of criteria for initially is for doing logical control delegation was the proximity based, that is RSI based, or load based. So at a high level concept, the logical handover process can be categorized into three steps. One is a discovery. What are the candidates available to which we can hand over? Then based on the information the controller has, it can select the best available controller. And then third step is to actually do the association. This is where the physical handover comes into place, where the link between the two entities is broken and new link is established. So we also have categorized logical handovers into two types. One is controller initiated, where controller decides handover should happen or not. Other one is vehicle initiated, where vehicle by default would initiate and not worry about controller's decision. Due to the time limitations, I'm just going to cover the control initiated handover workflow. The controllers periodically send beacon messages to the vehicles. Once the vehicle receives the beacon message, they calculate the RSI and the packets lost for the respective controllers. Then they update the controller with the information saying that this is the RSI I'm getting from you and from the neighboring controllers and other kind of metrics. Based on the information received by the vehicle, the controlling controller decides, has the criteria for handover been met for this vehicle or not? So for example, if it is RSI based, they will check the RSI value which is being sent by the vehicle. If it is load based, they can check what is the current load which the controller has, and is it okay if they could hand over a vehicle to some other controller. If the criteria is met, then the controller sends this information to the vehicle saying that I am giving you the target controller where you need to initiate the request for handover, and just go and initiate the handover. So vehicle goes and initiates the handover. The prototyping which we did is like we have three types of entities. One is the controller, which is just a plain RU STN controller. Then we have the tertiary controllers, which are like which can have both switch, which is the OVS, and the controller, again the RU controller. We have plain vehicles which are acting just as OVS. Then all these applications are running on top of MiniNet Wi-Fi. MiniNet Wi-Fi supports all different kinds of protocols. I would like to emphasize here that we added PubSub module into MiniNet Wi-Fi so that we can support east-west communication across controllers. So for the scenarios, we decided, okay, we need to have some kind of benchmark to benchmark our D2ITS application with. So we decided that we will have one scenario where we will have one entity, that is the one controller, co-located with an LTE base station, and there will be one vehicle which sends periodically the emergency and the information messages across to the vehicles in this domain of this E-node B. As you can see, it has a constant latency. There's no distinguish between the warning or the emergency message, and the latency is flat at 142 milliseconds. The reason for that is because for LTE, no matter where the location of the two vehicles is, even if they are adjacent, it still will go to the backhaul and come back to the vehicle. So there is no concept of an edge in this case. Then we ran this kind of a similar experiment where we have a vehicle which sends periodically the information and the warning messages and moves across two different RSUs. In this case, we have vehicle 4, which is sending these messages, and we are taking the results or the report of latencies from the vehicle 6. So as you can see, when the vehicle 4 was in the domain of vehicle A, it saw a higher latency because the message for the information message, because the message had to travel through the data plane traffic of the RSU A and the controller A, and then go to controller B, and then from controller B go to vehicle 6. But as the vehicle 4 kept moving closer and closer to domain B, the latency started reducing because now there is no hopping of the message from one controller to another controller. So the information message latency reduced at around 148 to 150 seconds into the experiment. As with the emergency message, you can see even though the vehicle was sending the emergency messages in the domain A, vehicle 6 never received the emergency message because emergency messages are only specific to a domain. Hence, for the first half of 150 seconds into experiment, there was no emergency message. But as the vehicle went into domain B, there is an emergency message. Then I'm showing another case of RSI based handover. In this case, we decided we will have only one vehicle, and this vehicle will go across through different RSUs, and it will send a ping message, a ping from the vehicle to an internet, maybe say Google DNS 8.8.8.8. So as you can see, the results, the main thing we want to highlight here is that even though you see the vehicle is going across, there is never a link breakage, and the latencies are almost all consistent around 20 to 22 milliseconds. You might see there are peaks around in between in this graph. The reason for that is because the way we have set up our experiments, there are cases where the vehicle is on the edge of one of the controller's domain, but there is no other controller where we could do the handover, hence these spikes. And as the vehicle moves closer and gets into the overlap zone where both controllers ranges are overlapping, the system is intelligent enough to do the handover and reduce the latency. So I have more experiments in this slide later on, but because of time, I'm just not going through them. Feel free to look at the slides, and there are results for the load-based vehicle-to-vehicle communication and smart rerouting-based example we did. To conclude, here we have demonstrated that we have a hierarchical and reconfigurable framework. It supports both low latency and increases the programmability, has lower overhead, and we hope that with this, the messages we have created in this framework can be added to ITS RHW framework. Thank you. That's the end of the slides, and I'm happy to answer any questions in the Slack channel. Thank you.
Excellent. Thank you, Anuj. Does anyone have any questions for Anuj? I'll go ahead and check the symposium minutes. I don't see anything there. If you have a question, feel free to unmute yourself. If no one else has a question, I'm just curious, Anuj, how your work, not how, I'm wondering whether you and Shesha have talked about how his need for a decentralized communication network and how that would be implemented in the D2 ITS. Wonder whether you've discussed that possibility at all. I mean, I can see that they're clearly related topics. I'm just wondering how much you've considered those sorts of applications. I think you're muted.
Yeah, sorry. So I think that's a very good question. While I was hearing Shesha talk about his work, it was like coming clear to my head that, okay, this kind of, we could use his application and run the same thing on D2 ITS. We have not talked about it, but we definitely, as I mentioned in my previous slide, that there is we also want to showcase this platooning of the vehicles, where there might be a set of vehicles which are just, they lose the network and they're just one platoon, and there will be one controller which can communicate across. That is the case we have and we support in D2 ITS, but yeah, we might have to sync with Shesha about this.
Yeah, great. Really interesting stuff. Does anyone else have any questions? Okay, if you have any questions for any of the speakers, feel free to update the symposium minutes slide later, and then we can get answers to that by the end of the symposium. Thanks, Anuj. I really appreciate your willing to present today, along with all of the other speakers. It's been really a wide variety of topics and really interesting stuff. And it's obviously a very large landscape to consider. So it's really interesting to hear about all the various projects that are all related around autonomous vehicles.
Thank you.
Yeah, thanks very much. And thanks.